Let ABCD be a convex quadrilateral with AB equals CD equals 10, BC equals 14, and AD equals 2 root 65. Assume the diagonals of ABCD intersect at point P, and the sum of the areas of triangles APB and CPD equals the sum of the areas of triangles BPC and APD. Find the area of quadrilateral ABCD. Let's first draw our quadrilateral ABCD. It has side lengths AB and CD are both equal to 10, BC is 14, and AD is 2 root 65. Since root 65 is just a little over 8, 2 root 65 would be a little over 16. Like 16.1 or something. So let's draw the quadrilateral ABCD. First, we have to draw AB and CD, which have equal length. They're both equal to 10. BC is equal to 14. And AD is equal to 2 root 65. The diagonals of quadrilateral ABCD, AC, and BD, they intersect here, point P, and we're given that the sum of the areas of triangles APD and BPC is equal to the sum of the areas of APB and CPD, and we need to find the area of quadrilateral ABCD. So what can we do now? Well, I think it would be easier if we just label the 4 lengths that are created at point P, in other words, PA, PB, PC, and PD. It would be easier. We can get a greater view of what's happening here if we label them little a, little b, little c, and little d. So what does the area condition mean in terms of A, B, C, and D? Well, we know that the sum of the areas of triangles APB and CPD equals the sum of the areas of BPC and APD. The area condition can be represented in terms of A, B, C, and D, and the intersection angle theta here, the acute angle formed by the diagonals of the quadrilateral. Let's call that theta. So we have that the area of triangle APB is equal to 1/2 AB sine theta. The area of triangle CPD is 1/2 CD sine theta. This is the sum of the areas of triangles APB and CPD. It's equal to the sum of the areas of BPC and APD. The area of triangle BPC is 1/2 BC sine pi minus theta, but sine pi minus theta is equal to sine theta. So I'll just write that, plus 1/2 dA sine pi minus theta or sine theta. So we can cancel the sine thetas. We know that 1/2 AB, we can also cancel the 1/2s. We get AB plus CD equals BC plus DA. That's the condition that needs to be satisfied in order for the area condition to work in quadrilateral ABCD. We need AB plus CD equals BC plus DA. We can rewrite this as AB plus CD minus BC minus DA equals 0. And we can factor this as AB minus BC. You know, that's equal to B times A minus C. And CD minus DA, well, that's equal to negative D times A minus C. So this is B minus D times A minus C. And this should be equal to 0. So all we need to have is that either B is equal to D or A is equal to C. So let's assume that A is equal to C here and see if we can continue from there. So we need to replace all A's with C's. Let's do that. I've only written one A here. Let's replace that with a C. And then use the law of cosines on triangles APB, BPC, CPD, and DPA. So when we use the law of cosines, we'll get some interesting equations that use A, B, C, and D. And we can proceed from there. So the first equation we want to write down is that C squared plus B squared minus 2BC cosine theta is equal to 10 squared, which is 100. We also have C squared plus B squared minus 2BC cosine pi minus theta, which would be plus 2BC cosine theta. Cosine pi minus theta is the negative of cosine theta, so that minus becomes a plus. It's equal to 14 squared, 196. On the other side, we have C squared plus D squared minus 2CD cosine theta is equal to 100. And C squared plus D squared in triangle APD, we have c squared plus d squared plus 2cd cosine theta equals 2 root 65 squared, which is 4 times 65, 260. So what can we do with these equations? Well, we can add the first two and add the second two, right? Because the negatives and the positives will cancel out, and we don't have to use cosine theta anymore. So we can do that with the first set of two and the second set of two. We have the 2b squared plus 2c squared is equal to 100 plus 196, which is 296. And the second set of two, we have 2c squared plus 2d squared is equal to 360. Now, what else can we do here? We could also subtract the first from the second to get an equation only in terms of BC and cosine theta, and we could do the same for the second set of two. You'll see what I mean when we do this. C squared plus b squared plus 2bc cosine theta minus c squared plus b squared minus 2bc cosine theta. That's a difference of 4bc cosine theta, which is equal to 96. And in the second set of two equations we have formed using the law of cosines, we know that 4cd cosine theta is equal to 260 minus 100, which is 160. So we can divide these two equations. The 4c's cancel out and the cosine theta cancels out. So we get d over b equals 160 over 96, which is 5 times 32 over 3 times 32, so 5 over 3. And from this side, we can just subtract these to get 2d squared minus 2b squared is equal to 360 minus 296, which is 64. So d squared minus b squared equals 32. And d over b is 5 over 3. So what can we do now? Well, we can let d equal 5x and b equal 3x for some positive real number x, so that 5x squared minus 3x squared is 32. And what can we do with that? Well, 5x squared minus 3x squared is 4x squared. That's equal to 32. So x squared is 32 over 4 squared, which is 32 over 16, or just 2. And therefore, x is equal to root 2. So d is equal to 5 root 2, and b is equal to 3 root 2. So going back to our diagram, we can update d and b with those values, 5 root 2 and 3 root 2. Now we still have to find c, but how are we going to do that? Well, we can substitute the known values of b and d into these two equations. Let's substitute it into the first set to see what we get. We got these two equations via the first set. So substituting the values of b and d that we found, we get that b squared plus c squared is equal to 148. So since b squared is 3 root 2 squared, which is 18, we have 18 plus c squared is 148. And therefore c squared is 130. And that gives c is equal to the square root of 130. So we can replace c with the square root of 130. And just to verify that c squared is indeed 130, we can plug it into the second equation here, which gives that c squared plus d squared is equal to 180. And since we know d is 5 root 2, d squared would be 50, so c squared would be 180 minus 50, which is also 130. Either way, we get c squared is 130, and c is the square root of 130. Now, what's the area of quadrilateral ABCD? That's what we're asked to find. It's 1/2 a plus c times b plus d sine theta. So we need 1/2 a plus c times b plus d sine theta. But a is equal to c, so we just do 1/2 c plus c, which would then be just c times b plus d times sine theta. And we know b plus d is 8 root 2, is 3 root 2 plus 5 root 2. C times 8 root 2 sine theta. So all we need to find is the value of sine theta now, because we know that c is equal to root 130. So in order to find sine theta, we need to find cosine theta. And we can do that by using the second set of two equations we found. 4bc cosine theta is equal to 96. So we know 4b is 12 root 2, because b is 3 root 2, times c cosine theta is equal to 96. 12 root 2 times the square root of 130 times cosine theta is equal to 96. And dividing by 12, you get that the square root of 2 times the square root of 130, which is the square root of 260, or 2 root 65, cosine theta is equal to 8. That's what you get after dividing by 12. You can divide by 2 again. You get root 65 cosine theta is 4. So cosine theta is equal to 4 over root 65. And we would get the same if we use the other equation. We still get cosine theta is equal to 4 over root 65. Because then d is 5 root 2. It's essentially just the same thing multiplied by 5 over 3. You'd still end up with the same value of cosine theta. So we get sine theta, which is what we want to find the area of quadrilateral ABCD, is 7 over root 65. And that's because 4 squared plus 7 squared is 16 plus 49, which is equal to 65. Sine theta is equal to 7 over root 65, and using this expression for the area of quadrilateral ABCD, which we found, the square root of 130 times the square root of 2 is the square root of 260, which is 2 root 65. So 8 times 2 root 65 is 16 root 65. And then sine theta is 7 over root 65. The root 65s cancel out. We are left with 16 times 7, which is 112. And that's the area of quadrilateral ABCD. Thank you for watching this YouTube video. Please follow my channel if you would like to see more videos. And please help us get to 400 followers before the AIME I on February 1. We're currently not on track to reach that level, so I've lowered the bar to 375. Please help us get to 375 followers before the AIME I, and thank you for watching this YouTube video.